the screencast for going over the energy homework problems. My bet is we should have done a lot of this in class, but if you were absent or if you would like to listen again, go over it again. That's what this is for. So these were assigned when I was absent, I believe, September 26th. Didn't give you much background other than posting a screencast with a couple example problems. All right, so I do want to go over these. These are the formulas we have. I notice here I'm using slightly different nomenclature or slightly different symbolism, I guess, rather than what's on your formula sheet. Your formula sheet says U-grav, U-spring, or U-elastic, K instead of KE, stuff like that. This one I think is consistent. This one I think is consistent with your formula sheet. Remember, for gravitational acceleration, or G, we can talk about 9.8 newtons per kilogram or 10 newtons per kilogram. For my solutions, I use 10. Physics classroom solutions use 9.8. That's why we might have a little bit of a difference. I try to remember to put in a different color of pen over here solutions if they use 9.8. And at any rate, so Lamar Grant, powerlifting star, became first man to deadlift 5 times his own body weight in 1985. Determined the work in lifting 300 kilograms, a total height of 0.90 meters above the ground. Well, first of all, that's ridiculous. That's less than 3 feet. If someone's doing a deadlift above their head, it might have been a midget. I don't know, or I can't even imagine what that would be. So the numbers are a little off, but you get the idea. So the work done is going to equal the change in gravitational potential energy. This person is lifting this up. So you can think of that as being work is equal to FD cos theta. The direction of the force being pushed is up. The displacement is up. So therefore the cos is going to be cos of 0 degrees, which is 1. So really we just multiply these together. How do we find the force? Well, it's the mass times the gravitational constant. So if you notice, when you're doing this, this really becomes this formula, mgh, which is the change in gravitational potential energy. So essentially, this is a sort of a specialized version of the work formula. Okay, so in other words, if you have something that's elevated a certain amount, you have a certain amount of gravitational potential energy. It took a certain amount of work to get that there. So anyhow, we just multiply those two together. mgh, 2,700 joules. If using 10 newtons per kilogram, 2,600 joules rounded if using 9.8. I hope you like these names that were from the physics classroom, hands full. Anyway, he's pulling upwards at an angle. So in this case, you need to be in degree mode, which I forgot, and you can see I've got white out here. So because they're pulling at an angle, I drew a little picture over here. We want to find the horizontal component of this. And therefore, it's not going to be 22.9 newtons. It's going to be 22.9 cosine of 35 degrees. It's going to be the horizontal component of force. We will talk about vectors for sure as the year goes on. This is the only time we'd use that with energy, really. So FD cos theta comes out to about 2,420 joules. For PC6 down here, and that stands for Physics Classroom Problem 6, in the problem set that I listed up here where there was a link. It's asking you to determine the work done by Nate Seifert. Apparently Nate has been bulking up because 102 kilograms is somewhere around 225 pounds. At any rate, if he elevates 2.29 meters in 1.32 seconds, the work done, again, is going to equal the change in gravitational potential energy. That's around 2,340 joules. Different amount if using 9.8. And power is actually really kind of important. It's the rate at which energy is transferred, or work divided by time. So 2,340 joules divided by 1.32 seconds, 1,770 watts. You're probably familiar with power ratings from things like light bulbs and hair dryers like have 1,500 watt power rating, stuff like that. So 1,770 watts, that's a pretty high power rating to go up 2.29 meters in that short amount of time. 25, analytical and NOAA formula. Again, physics classroom names. Give a 1 kilogram cart an initial speed of 2.35 meters per second from 0.125 meters above the lab table. Determine the speed was located 0.34 meters above the lab table. So in this case, if we know energy is conserved, and we think there's minimal friction, the total initial energy should equal the total final energy. Well, the way they've given the numbers here, you have initial kinetic energy, initial gravitational potential energy, and therefore we'd expect that at the end as well. So I'm writing down initial big idea, type of formulas, or pardon me, the types of energies, and then the formulas that go with those energies. Now, in reality, you probably could have set this as a 0, and this would have been 0.340 minus 0.125, would have been the same value. Doing that math compared to doing this math didn't make much of a difference to me, so I didn't change it. But really, remember with potential energy, you can choose your zero height. So overall here, I plug these numbers in. I get 2.76 joules of initial kinetic energy, 1.25 joules of initial potential energy, 3.4 joules of final potential energy, and the rest is left as kinetic energy. That's 0.61 joules. That's going to equal 0.5 VF squared. So get about 1.1 meters per second. I have got to find a better scanner in this school than my phone, because these are kind of not showing up great. Anyhow, Nolan Ryan had the fastest pitch in baseball. You may think more modern people might have it faster, but I'm not sure they measure exactly the same way. Anyhow, clocked at 100.9 miles per hour, 45 meters per second. If he directed it directly upwards, what would be the maximum height it would travel? Think energy. So initial energy is kinetic, final energy is gravitational potential. You might think you need to know the mass of the baseball, but if you look, the mass is on both sides of the equation, therefore it would cancel out. If you put a dummy number in, it would also cancel out, so it doesn't matter. So we end up getting around 101 meters, 103 meters if using G is 9.8 newtons per kilogram. For 12, skydivers dropping at a certain altitude and has a certain speed, finding the kinetic energy, finding the gravitational potential energy, I'm assuming relative to the ground, total mechanical energy is those added together, and then finding the final speed and the very unfortunate incident if there's no air resistance and no parachute. Notice how much faster that is, because all that mechanical energy at the end is kinetic energy just before the person hits the ground. So these are the numbers in blue here if we use 9.8 newtons per kilogram. PC21, which is slightly modified as well. By the way, this last one, I believe, was modified. It wasn't on the physics classroom site. So top thrill dragster. They have not, that has been off limits or not used the last couple of years. I hear they're bringing it back, but it definitely had a lot of mechanical issues. Designing rides for amusement parks is quite high tech for a variety of reasons. So Kennedy Wells, again, sadly Kennedy, you do not weigh 225 pounds, but those were the numbers given, and I decided to use student names. At any rate, you're not moving initially, so there's no joules of kinetic energy. So it sounds like this thing is accelerated at ground level and then zooms up a vertical section. So the acceleration is on the ground level. At the end of that time, she would be moving at 53.6 meters per second. So that would be about 147,000 joules. The height that would cause her to go, if she's going up 420 foot, the vertical section is 128 meters. And so therefore at that point, she would have 131,000 joules, MGH, of gravitational potential energy. That means she'd have 16,000 joules of kinetic energy left, and therefore she would still be going 17.7 meters per second upward. So that might not make sense, but at the top, at the end of the vertical section, it starts to angle. It's still going upwards, but not vertically upwards. So these are the numbers you get if you are using 9.8 newtons per kilogram. Anyhow, hope that helps, and hopefully we go over some of those in class. Thanks.